Yeah, hi everyone. My name is Gurgen. I'm from FHE. And today I will talk about FHE Computer and about FHE in general. This is agenda of my talk. I would like to provide some information about FHE problems for developers. In the second part of my talk, I would like to cover FHE Computer via building a FHE and go through use cases. So let's start with FHE. What is it? Basically, it's the form of encryption that allows us to make computation of encrypted data. Basically, usually two operations considered addition and multiplication, just because with addition and multiplication we can have fully Turing basis, which means that we can evaluate arbitrary functions. And the regular case, the regular example provided in the literature is we have client, we have server, client have data, client wants to send data to the server, ask to evaluate for evaluation some function, server evaluate this function, send back result, client decrypt the result. The story started in 1978 with the work of Rivest, Adalem, and Deutsches. The name of the work is on data, banks, and privacy homomorphism. The authors firstly asked about opportunity to evaluate some function of encrypted data. And it was in 1 year after inventing RSA scheme, the same authors, and RSA by itself what we call partially homomorphic, because RSA supports homomorphism on multiplication operations. We talk about fully homomorphic encryption, but there are different types of homomorphic encryption. Fully homomorphic encryption is the most powerful one because it allows us to make arbitrary computation of encrypted data. But there are 3 additional types usually considered. The first one, the most simple one, is partially homomorphic encryption, where we have homomorphism only regarding one operation, like addition or multiplication. We have somewhat homomorphism, which allows us to evaluate both operations, but only for a certain subset of circuits. We have leveled homomorphic encryption schemes, which is more powerful than previous one, because with leveled fully homomorphic encryption schemes, we can evaluate arbitrary function, but we need to know the depths of computation. So if you know the circuit, if you know the depths, you can choose the parameters that will allow you to evaluate arbitrary function. The problem with this type of homomorphic encryption is that you can do unlimited operations. You need to choose the level, the maximum level of operations, and your scheme, your encrypted data will be suitable only for these parameters. And the last one, the most powerful, is fully homomorphic encryption, which allows arbitrary computation, unlimited, you can do everything you want. This is just some milestones, important points in homomorphic encryption. The first scheme and the question, which was the partially homomorphic, was in 1978, as I mentioned. The first fully homomorphic encryption schemes we got in 2009. And at this timeline, you can see the most popular, the most powerful FHE scheme that is used for now. Most of the modern FHE schemes, old schemes which were mentioned on the previous slide, based on the problem which is called learning with errors, LWE, and its extension for ring LWE. Invented in 2005 by Oded Regaf. And for nowadays, we have different schemes, and we don't have, unfortunately, we don't have some universal FHE scheme that will be suitable for everything, for all kind of tasks. Each scheme has limitations and advantages and limitations. Some of them support packing, some of them not. Some of them support fast bootstrapping, some of them not. And depending on what you are going to build, you need to choose the right scheme. The same about libraries. So for now we have a bunch of FHE libraries. I just presented a few ones. The most popular one, I believe. They differ from schemes supported, they differ from languages supported, and license. For example, OpenFHE, Latigo provide implementation for different schemes and provide quite fair license, which don't restrict you to use it for commercial use. TFHE is focused only on one library and has some commercial license. You can't use it for your commercial goals without some agreement with the owner. And the C library I just mentioned to show that we don't have some universal library, and C library is a Microsoft FHE library, which is not supported. Okay, it's about just FHE in general, and let's try to think from developers' point of view and how it's difficult to build FHE applications. And we believe that there are three main issues for developer. The first one is limited basis of operations, because any FHE scheme by default supports addition and multiplication. Depends on the scheme, maybe some additional operations, but it's not as in the world when you work with open data. You can do a lot of things. You can do comparison and get result in open form, which means that you can't have branch, you can't have some loops. Performance is also the bottleneck, but we see great progress in performance, and we believe that performance will be improved, and also in coming years we will have great performance which will be suitable for most of the use cases. But despite this fact, we already have a lot of use cases where FHE can be used, because not all use cases require to get result immediately. Sometimes, for example, when we talk about some inference and you would like to analyze some medical data, you can send your data in encrypted form and just wait for 1 hour or 1 day or a few days. It's totally fine. And here performance is not the big issue. And the last one is the lack of developers ecosystem, because despite the fact that we have different projects, we have different libraries, we have different atoms to build FHE compilers, we don't have, I believe it's just my opinion, we don't have some great solutions that will cover all needs from developer side. To understand these problems more clearly, I like to consider the real use case based on privacy preserving ride hailing, and just let's imagine we would like to build privacy preserving ride hailing. This is how it works when we work with open data. Simplified version, 3 stages. At the first stage we need to find the nearest car to the passenger location. During the journey the passenger or driver just need to send location. At the end of the journey we need to evaluate the price, which depends on 3 main things: the length of the track of the journey, toll roads, and some specific tolls area. And when we try to implement it, when we try to bring privacy at this service and build privacy preserving ride hailing, we will realize that we need to solve a few subtasks. This is just one of the first example. At the first stage we have encrypted location, pickup point, and we have encrypted driver's locations. We can't have driver locations in open form, because otherwise server, it will be quite easy to determine the position of the passenger. This is why driver locations should be encrypted. And we have one point in encrypted form, we have set of points in encrypted form, and we need to make matching. Another problem during the journey, we need just send encrypted form, but if we do it with FHE, we have the problem with performance, because FHE ciphertext much more bigger than let's say RSA and any other not FHE schemes, but it's not the big deal. The most difficult part is after the journey, where we need to evaluate the price of the journey, and we need to solve at least 3 tasks. We need to evaluate the journey track, we need to evaluate interception between track and toll areas, and also we need to find interception with toll roads. And the problem here is that during the evaluation, during the solving these tasks, we will need to evaluate some functions like square root, division, addition, but we can do only addition and multiplication. And it's not obvious how you can evaluate square root function if you can do only addition and multiplication. For sure, the obvious approach is to use some polynomial approximation. But the problem here is that it may be too expensive. At the same time, it may be not so accurate, and sometimes it's not the good deal. And also, it's not so easy to build polynomial approximation, because, for example, if we work with one variable, we can use some Chebyshev approximation. But if your function depends on n-dimensional function, it's not so easy. What can help us at this stage? For us, as for developers, the really things that can help us is, we call it FHE components. The idea is that it's just building blocks that can evaluate certain functions on encrypted data. And we believe that with component-based approach, development of FHE application should be and must be much more easy. And we utilize this approach in building our ecosystem. And I will be happy to share more how it works. Here, just an example of FHE components. So it's some you can consider, as developer, you can consider it like some black box, which can take as an input some encrypted data, evaluate some function, provide result. So for example, sine, relu, cosine function can be considered as FHE components. And if we have these components, a lot of things will be much more easy. And in this world, and basically, when we talk again about FHE applications, all FHE application, after some lowering, can be considered as the circuit of FHE components. Some components can be run simultaneously, parallelized. Some components depends on each other, but generally speaking, any FHE application can be considered as some circuit of components. Depends on components type. Sometimes we need to connect components because components may be based on different FHE schemes, and there are great direction in FHE which called scheme switching that allows us to use one scheme for some certain computation. For example, we can utilize CKKS for computation of approximate on the real data. Then, if we need to make some comparison, we can just make scheme switching and transfer ciphertext from CKKS to ciphertext in TFHE scheme, which is more suitable for comparison operation. Make comparison operation in TFHE and then go back. Another important part about the bridge is that not necessarily the output of one component is suitable, can be used as an input for other components. Sometimes we need to make some additional works, repacking, resorting, etc. to provide this composability. And on our side, we're building components library for developers. We call it polycircuit. And the idea is that it's just rich set of FHE components you can use. The problem with building such library is that to build this library, we need to engage community because each component usually is state of the art and is generally true about FHE in general. When you build some application, it requires domain-specific knowledge. It requires a lot of things around it. And just building components library inside one company doesn't matter. Is it Microsoft or is it some unknown startup? it's not possible. You are very limited on resources. You can't provide, let's say, more than 25 components per year. You can't support it well. And to accelerate this field, to engage community, we developed a challenges platform, which allow us to publish FHE challenges to building some components, automate all validation process, engage community to participate, provide some bonuses, and utilize result as open source components. So we launched this platform last year jointly with OpenFHE teams. We already have challenges on the platform from IBM, from our team. We already got more than 10 FHE challenges completed. Results we have better than all existing approach before, and everything is published open source, and everyone can use it. Interesting thing about when we talk again about FHE development, when we talk about FHE application is, okay, I have components, I have libraries, but how I need to use it. And this is why we need the FHE compiler. And on our side, we build our own FHE compiler because we believe that compilers we have right now are either limited in operation supported. For example, there are compilers that focus only one certain FHE scheme or library. And good example is Seal Microsoft library. If you build your compilers that focus only one library, it doesn't matter is it some open source unknown library or it's library from Microsoft, it can be unsupported in one day. And another thing that you can't be focused only on one scheme. We need to provide developers opportunity just to write your FHE application without knowing anything about FHE under the hood. And here just of the example of some FHE function on our language. The idea is that you work as before, you work as on, let's say, a Rust language, and you just utilize secret type, it's some wrapper around regular type. And you just, with secret, you can just mention that this part should be encrypted, this part will be private. And everything out of this box will be done by compiler. And building our compiler based on MLIR stack is the great project from LLVM. And the idea of MLIR is to have not only one intermediate representation form, but instead of it to have multi-layer intermediate representation forms. In our compilers, we choose this infrastructure, this structure of layers. At the top layer, we have polycircuit layer. This is the layer where we work with FHE components. We do some optimization around components, lowering. The second layer, we utilize secret dialect from HAIR. HAIR is homomorphic encryption intermediate representation compiler toolchain from the Google open source. At the early stage, but already provide a lot of interesting things. We utilize our secret dialect based on HAIR dialect. Then we go to batching layer, because again, as I mentioned before, different schemes can support batching. And with batching, we can achieve much more performance, especially in FHE. Then we have scheme-specific layer, where we work with different schemes. And in our compiler, we can utilize different schemes and integrate scheme switching, which allow us to build application which will not be focused only on one scheme. Then the layer, which is not necessary to use this layer, but the next layer is polynomial, when we lower everything related to scheme just to polynomial arithmetic. Why we do it? It also inherited from HAIR project, and it allows us to make lowering from this layer directly to LLVM-IR, which means that after LLVM-IR we can just go to any supported backends. And at the same time we can go from scheme-specific layer to FHE library. We can generate FHE code depends on the library. We can generate the code LVMIR, and we can generate the code for our virtual machine that can run and evaluate FHE computations. This is about development side, and now I would like to provide some information about our main product, which is FHE Computer. And Firm's FHE Computer in our side, it's a decentralized network of heterogeneous nodes that can make computation of encrypted data. It has multi-layer structure. At the top level, we have application layer, which can be considered as some kind of front end of our application. The second part is orchestration layer, which is responsible for everything around delegation tasks, managing tasks. We have order book, dynamic order book, and the orchestration layer work with order book. Verification layer, I heard today a lot of talk about ZK, and in FHE we need verification because we work in an environment where everything can be considered as malicious. And the point here is that ZK is not enough at this stage. We can't use just ZK to prove everything we need. Simple example, if I want to send some of my data to some server for computing some function F, to be able to use, and I consider server as the malicious attackers, adversary. And if I want to have some proof that computation was done correctly, I need to know the algorithm. The algorithm of computing function F should be public. If not, and it's the case, because sometimes you don't know the algorithm, and a server would like to keep the algorithm private. We can't use ZK, and we need some other techniques. Execution layer, which consists of Firm's actors, which provide computations. It's important that this layer consists of heterogeneous actors, because some actors may be focused on some specific tasks. So for example, we can have actors who can do fast matrix multiplication, and that's all. At the same time, we can have some general actors who can evaluate everything. And in our world, we really need data layer because it's not possible to store data on chain. And this is why, and not only because of this reason, we need separate data layer. In our case, it's IPFS-based data layer, and all communication with data go through this data layer. FHE market, as I mentioned, is the top level in our computer. This is just front end, the place where you can deploy your application. At the same time, you can use some applications. And let's consider how it works when I want to run some application. Let's consider I'm some of the user. And I try to run application. At the first step, orchestration layer builds some execution graph. In this case, it's just all task depends, so it's not parallelized version, but potentially, if there is no some dependency between different orders, it's possible to run it simultaneously. Orchestration layer create these orders. We have two types of order. It may be call for evaluating some components. At the same time, it may be custom component, which includes just some code for our virtual machine. Then these actors, these orders aligned, delegated to some actors, and to provide some resistance, we also use fallback actors. And usually, let's say these two actors responsible for evaluating these components, and on our side, on blockchain side, it's not needed to manage the state of the main actors. Instead of it, actors in the pair just control each other. And all of them has access to data layer. This is just a small example how order looks like. This is simplifying the code for our virtual machine, and you can see that order to is just the order to call some components, and it means that if I'm an actor and I'm committed to evaluate relu function or relu component, when I got this order, I can do different, I can implement this order in different ways. First of all, I can just take implementation for relu function from polycircuit library and go through this code. At the same time, I can develop my own implementation, and this implementation may be private. I don't want to share it. It will be fine for us. The only thing you need to provide as the actor is that you get the result and you provide the result which was expected. Interesting thing about ecosystem that we provide great opportunity for developers to monetize some small contribution. The idea that all applications on the market side, on the application layer, build based on the components in polycircuit FHE library. And the idea is that if you, let's say, develop good component, let's say relu as before, which is faster and better than components we have inside our library, you can just come and say, okay, this is my components, I would like to utilize it for other applications, and then if your components integrated on our polycircuit library and some applications use your components, you will have some royalty from launching these applications. And here, where Therma plays different role, because we need somehow to benchmark components, and we need some fair way how we will integrate new components in library. And the idea is that if some developers develop new version of components, they just go to Therma platform, upload to Therma platform. On the Therma platform, we make all tests, and then if everything fine and result better than the one we have in our library, these components will be integrated in polycircuit library. And the last things I want to mention, use cases. Usually for FHE, this is the most popular use cases. You can see around all projects focused on FHE, dark pool, privacy preserving AI, and private DeFi. And it's great, it's really great use cases. For me, the best one is privacy preserving AI, because with FHE, it's not just bringing privacy in existing solution. With FHE, we can unlock a lot of data which is not now possible for utilizing for AI. And we can, on our computer, we can build applications for all these kind of things. But for us at this stage, the main use case is this one. We are building, and we already built on top of our computer, vector database. And interesting that this database require this infrastructure that we provide, because it's very hard to launch vector database just in cloud version, based without multi-scheme approach, based without heterogeneous actors. And in our case, it works. And that's all from my side today. Thank you for your attention and time. Can you answer any question?
Thank you for your talk. Are there any questions?
Thanks for the talk. I have a question about the actors or the FHE components you have. Your computer scheme has already implemented or achieved. Does it include the array positioning as in a data storage to locate or to fetch a value from a list or array to how you achieve that component?
Sorry, I'm not sure I got the second part of the question.
I mean that have you achieved our component, our FHE component that to fetch a value to get the value of an array or a list, such component, how we achieve that?
Do we achieve some components that are helpful to build the database and build some useful, right?
Yeah.
Yes, we already achieved some components. Some part of them just published, open source, but we already have at least 20 components that we are also going to publish, which allow us to build a lot of things around vector database and build a lot of stuff around EM.
Okay, so you have published something about this component. So could you please provide a reference to such publication? It will help me to see your your solution to that.
Sorry.
Oh, sorry about that. I mean that could you please give me a reference to the publications related to such components?
A reference to applications that relates to such components?
Yeah.
So for example, when we talk about vector database, the core part of database is evaluations of metric functions. And the quality of your metric functions determine the quality of your AI model. And each metric function will already support at least 5, if I remember correctly, metric functions as the components can be utilized. At the same time, different activation functions for AI. Another components for, let's say, IBM launched the challenge on our platform, and the challenge was about building components for evaluating parity of the last bit of the parity of the number. And it's also very useful because if you can do it, if you can evaluate parity, you can build what's called lookup table. We also have challenge for lookup table, which means that you have, let's say, encrypted array of numbers, and you would like by encrypted index to get some value. And this is just some examples of components that can be used.
Okay, I got. So the main idea to do that is lookup table. I got.
Lookup table and other components.
Oh, lookup to another. Oh, sorry about that.
Activation functions for the
activation functions.
So, for example, ReLU is a popular activation function when you build neural network.
Yeah, to help utilize FHE friendly database. You mean that?
It also used in FHE database, but it mostly used for AI, for neural networks, as an activation function. Because in neural network, with FHE, you can easily evaluate a weighted sum of inputs, but the problem how to evaluate activation function on this input, because it's non-linear functions, and it's not clear how to build it when you can do only addition and multiplication. And it's state of the art, how to build it.
Okay, I got. I need to hear more about that. Okay.
Thank you, Paul.
Thanks everyone. Give me this content. Thank you very much.
Here, I think you were first.
Yeah, thanks for the talk. Yeah, you mentioned using MLIR, and in RISC-0, they are also using MLIR to compute polynomials for the zero knowledge. I was wondering also if there are common libraries that you use or common techniques.
Common technique about what?
With the RISC-0 project and the others.
I am not an expert in ZK compilers, and I don't very well know how they structure it, but I know that polynomial arithmetic, polynomial layer should be similar. But at the same time, in the FHE, there are some difference. And for sure, there is some interception, there is some similar work, but there are also different stuff, because there are different types of polynomials, different optimizations.
Okay, and then you first.
So first, very nice slides, and I was wondering if it's usable in real life, like will it take more than a minute to do an addition, or is it already fast enough to build something with it?
Addition is fast enough. You can do addition super fast, but what you can do with addition, there are again, in my background, we build real-world use cases. Privacy concern is just one of the examples, which is fast enough to be able to be integrated in reality. So it's not about hours. So just for example, for Uber case, when you have encrypted track and at the end of the journey you would like to evaluate the price based on CKS scheme, we build solutions that takes less than 30 seconds to evaluate track distance, and then evaluate toll roads and toll travels. And these three parts is totally independent. You can do it simultaneously. So this is why the most expensive part was around 30 seconds. At the same time, there are use cases where it's very expensive, and now you can use it.
Yeah, so that's for the non-fully homomorphic encryption, or is it for the fully homomorphic?
For fully homomorphic. Now, in general, if you need some immediate, if you send request and you need immediately get a result, homomorphic encryption is not a good choice for you, because it requires sometimes. But if we in Web3 world, in most cases it's not the case. You can wait. In AI, also in the most part of AI, you can wait. You can wait more than 1 hour. But at the same time, there are applications where you need to wait for a while, for years. But here we believe that hardware acceleration, we believe that we will have total new FHE schemes, because I mentioned that all schemes based only on the same problem, LWE. And also FHE components can help us, because with our approach, when we build, let's show this one, challenges platform. So for example, we published challenge for lookup table, and the first result we got took, let's say, n seconds. It was less than a minute, but anyway. After some competing process between participants, we finally got result that, let's say, x20 faster than initially. And this is also important thing about this platform, because with this competition-based approach, we can have here constantly updatable core with pair modeling.
Thank you very much for the nice presentation. It was great to get into the world of FHE, but as an AI developer, for example, I am very curious what would be a typical use case where I would go, like, as I'm familiar with FHE, I would be like, yeah, this is a use case to use an activation function as a component in FHE. Like, I just want to understand the use cases for like AI and machine learning.
For me, the most interesting use case when we talk about AI, you have different data sets relates to different data owners, and you can combine it in open form. So let's say different banks, and now all banks, each bank should train their model inside based on only their data set. With FHE, potentially you can combine all these data sets and build much more powerful AI model. Here there are another problems, because if you have different data, what about key? Who will be the owner of the key? But now we also have solution, which is threshold network. The idea is that we have some general key which separated through validators, and this threshold network is responsible for the encryption process. I believe that current solution is not safe enough, but we also working in this field, and at least there is solution how to solve this issue.
Okay, and if you consider the banks as like actors, their kind of database wouldn't be exposed in this case, but their, like, the knowledge of the database would still be preserved in the model. And wouldn't that still be like not anonymity problem, but like data leakage problem?
It's another important and interesting question, and it's also state of the art and can be solved on AI or FHE level, because it depends on the case. For example, again, if you talk about ride-hailing service, you can encrypt everything. So track is encrypted, areas is encrypted, drivers is encrypted. But if the price let's say from city center to airport, is fixed, you can just based on these additional factors extract a lot of information. And this is, you can solve it. You can say that I solved this problem with a free chip. But it's important part. It's the part for investigation depends on the case.
Yeah.
But very good question.
Thanks a lot.
I think just an input regarding to this question as well. There's also the possibility that you deploy differential privacy on the training of these models, and then if the privacy guarantee, differential privacy is strong enough, then you would not leak private information on the model. That's a potential solution. But also regarding machine learning, you mentioned the possibility of hardware accelerators, and you also mentioned the fact that if you want to do inference quickly, there would not be an ideal technology, FHE in general. Do you think that maybe these hardware accelerators would improve on this? Do you expect that to be?
I said a little bit different. I said that if you need to get result immediately and you don't have time to wait, FHE now maybe not the good choice, but not for all cases. For sometimes we have. About hardware acceleration, I believe that we have at least two directions how we will improve it. The first one is hardware acceleration. The second one is algorithm level. So it's about improving FHE scheme. Maybe tomorrow we will invent total new FHE scheme, which will be based on the problem that don't require such a lot of computation.
How much X do you think hardware acceleration is going to bring in terms of inference? Like, do you think it's 100x faster, 1000x faster?
You mean now, or how we expect it?
With the expectation of the hardware accelerators.
Compared to now, right?
Compared to now, yes.
The numbers I have, again, based on some companies who work in this field, they expect to have at least 25x acceleration in coming years. But like this.
Coming years being less than
3, 4.
3, 4 years.
But it just maybe recent research I saw for these numbers, but I need to check maybe another project expect more computation, because I personally expect improvements more from algorithmic side than from application layer.
Okay, thank you very much for the time.
Thank you.
So, can you hear me? Thank you for the talk. I just wanted to know on a high level how you would disrupt the cloud industry if you would do so.
How we
would you disrupt the cloud industry if you would do so?
Cloud industry in general, you mean just cloud industry in Web2 world?
Yeah, high level.
We cover both world, Web2 and Web3. Just why we are focusing on Web3 right now, because there is more demand, everything much more faster, and there is no some regulations that can provide some restrictions. But we working with Web2 companies, with Web2 use cases, our partners, our OpenFHE teams, with them we are working on a lot of Web2 use cases. And vector database I mentioned as the main use case for us is for both. So it can be used for Web3 and for Web2. And to be honest, for Web2, it's more suitable, I would say, because now we have more demands from Web2 world on this tool.
Any more questions? Okay, then thank you for the talk again.